In this video, we're going to look at integrating functions which are in a non-integratable form. So when you're given a function to integrate, it's either ready to integrate, in which case we say it's in an integratable form, or if it's not ready to integrate, we say it's in a non-integratable form. The challenge for students is not only performing the integration, but it's learning what is and what is not integratable and turning those non-integratable forms into their integratable form. And that really comes down to exponent rules or indices rules. So if you're not sure about the indices rules, the exponent rules, or not seen them in a while, you might want to check those out before you get into these non-integratable forms. Or just follow along here, because we're going to see a lot of those rules in these questions. So we're going to work these 6 examples, and then I'm going to show 3 further examples. And these are just good examples of the common types of things that are non-integratable, but we can't hope to see every single non-integratable form. There are thousands of them, but if you can learn some of these non-integratable forms, then that is good for a whole bunch of question types. So let's just make a start on these questions. So this first guy here, 5 over x cubed, that's in a non-integratable form because the form that we're looking for is the form ax to the n, and it's the same with differentiation. When you come to differentiate a function or integrate, you're looking for every term to be in the form ax to the n. So in other words, number x power, and the number in front and the power, they can be fractions. They don't have to be whole numbers, but they've got to be numbers in this form. So any deviation from that means that you're in a non-integratable form. For example, square roots or an x term on the bottom of a fraction. In fact, all of these are in non-integratable forms. So starting with this guy here, the x term is in the wrong place, so we need to bring it up to the top of the fraction so that it's ending up in front of the 5 in this case. But remember, this is not the integration. This is only an exponent rule to make the function integratable. So we still need to keep our integral symbol when we perform this first line of working. So this will become the integral of 5x to the power of minus 3, because when you bring a term to the top of a fraction, the power, the exponent changes from a positive to a negative, or from a negative to a positive. So this here and this here are the same thing, just written in a different form according to those exponent rules. But this is now in the correct format for integration, so we can go ahead and integrate. Remember, the integration power rule says increase the power by 1 and then divide by the new power. So the 5 is just a coefficient, so we can just leave that there. We're going to increase the power by 1, which goes up to a minus 2. It's very tempting to make it a negative 4, but it's a negative 2 because you're adding 1 to the power. And then we're going to divide by that new power like this. Remember also, this is an indefinite integral, so we need a constant of integration, a plus c on the end. And sometimes that will be the final form, but generally teachers will encourage you to take a negative power and turn it back positive, which you can do by the reverse of this rule. So we took the x term to the top, now we're going to take our x term back down the bottom, and it's good practice to do that, to put it back as a positive power. The 5 over 2 with the negative, I'm just going to write as negative 5, well, like the negative in front. So it's going to be negative 5 over 2x squared plus c. So that final step there, that's not anything to do with integration, that's just purely putting this x term back with a positive power for our final answer, the final form. Okay, so that's the first one. That's a very common form, having an x term on the bottom of a fraction. This one's kind of similar, but we can see there's a number on the bottom of the fraction as well. The big mistake students make here, they want to bring the 5 to the top. You don't need to bring the 5 to the top. We can just actually think of that 2 over 5 as being the fraction 2 over 5. So 2 over 5 in front of the term x to the minus 4. Because when you bring that x to the top of the fraction, it becomes x to the minus 4. And 2 over 5 is, just a fraction 2 over 5. So that would be this term now put into this format, in other words, put into an integratable form. So we can now go ahead and perform the integration. So increasing the power by 1, we're going to get x to the minus 3, and then we're dividing by that new power, so dividing by minus 3. Again, remember your constant of integration. Looks a little bit ugly, this. You've got a fraction being divided by a whole number, which is quite common in integration. So in this scenario, you can multiply that whole number, the negative 3, onto the denominator of your fraction. So this would end up being, and we can bring the negative in front, in fact, so this would end up being negative 2 over 15 x to the minus 3 plus c again. And then we can bring this x term to the bottom of our fraction to put the power back as a positive. So a little tricky, but this would end up being negative 2 over 15 x cubed, and then we've got our plus c there on the end. So again, similar, these are similar. This one's a little trickier because of that number on the denominator of the fraction, but it's quite a common form that, and a lot of students tend to get a little muddled with that one. Okay, moving on to the next example. So the issue here is a square root. This term is fine. It's in the form ax to the n to match the form we're looking for. This is not in the correct form. We're not allowed to have square roots or any other type of root. So we need to manipulate this in some way. And the way we can manipulate it is by remembering that using exponent rules, a square root is the same as a 1/2 power. So this is effectively 3x to the 1/2 power. The second term is fine. We're just going to leave that. Just be careful not to integrate the second term at that point. A lot of students do that. They'll manipulate the first term, but they'll forget that they're just using an exponent rule, and they'll go ahead on the same line of work and then they'll integrate the second term. But you can't do that. You've got to just get them all integratable first and then integrate them together. So we're going to increase the power by 1 and divide by the new power. So when you increase the power on a 1/2 by 1, it goes up to a 1/2, otherwise known as a 3/2. And then we're going to divide by 3/2. With the second term, the power goes up to a 3, and we're dividing by 3, and again, plus c on the end. We could tidy this up a little. So dividing by 3/2 is the same as timesing by 2/3. So we're going to end up here with 3 times 2/3, which is just 2, because the 2 3's cancel. So this term would end up just being a 2x to the 3/2. Second one's fine. Only thing we could do if you wanted, you could bring the 3 in front, the 2/3 in front to make it 2/3 x cubed plus c, like that. So square roots, in fact, any type of root, it's not only square roots, any type of root is really common as a non-integratable form. Okay, let me just make some space here. This guy is fairly similar. It's just that instead of a square root, we've got a cube root, and instead of just having an x, we've got an x to the 4, but a similar kind of genre of problem. So a cube root is the same as a 1/3 power, and the x to the 4 is just an x to the 4. So we can combine that 1/3 power. In fact, let's do that over 2 lines of working. So that would become x to the power of 4 to the power of 1/3, because a 1/3 power and a cube root are the same thing. Then there's an exponent rule that says in this scenario to multiply your powers together. So that would become the integral of x to the power of 4 times 1/3, which is 4/3. Like this. And you can skip that line. If you get used to these, you'll realize that whatever type of root you've got, that's going to become the denominator on your fraction on the power, and whatever power is already on the x term will just be on the numerator. So this is now in the correct format. We don't have a number explicitly in front, but essentially we've got a number 1 there, so we've got it in the ax to the power of n format. So we can go ahead now and integrate. So increasing the power by 1. So let's just think about that for a second, because that's a common scenario. So we're trying to increase the power on a 4/3 by 1. So it's 4/3 plus 1. To add a whole number to a fraction, you need to make the whole number into an equivalent, a fraction with an equivalent denominator. So that 1 becomes a 3/3. So in total, this is going to become 7/3. So when we add 1 to that, it becomes x to the power of 7/3. And then we divide by the new power, so dividing by 7/3, and we've got our plus c on the end. Dividing by a fraction, again, we can flip it and multiply by it. So instead of dividing by 7/3, we multiply by 3/7. So it becomes 3/7 x to the 7/3 plus c. So lots of little tricks going on there. So keep an eye on when you've got a fraction and you're adding 1 to it. Remember to turn that fraction, that whole number, the 1, into an equivalent fraction. And when you're dividing by a fraction, which is a common scenario in integration, you can flip it and multiply by it instead. Okay, so this one's got a combination of issues going on. It's got a fraction with an x term on the denominator, and it's also got a root there. So we've got both of those issues to overcome. So the first thing I think we'll do here, we'll change that root to a 1/2 power. Pretty much a no-brainer that when you see a root, you want to change it to its equivalent fractional power, because you can't then use any other exponent rules until you've done that. So we've done that, and then we've still got this issue of an x term on the denominator, but essentially here we've got an x being divided by an x to the 1/2, and that's going to allow us to use our divide exponent rule. The divide exponent rule says subtract your powers. So this power here on the x, remember, is actually a 1, even though we don't write the 1, it is a 1. So we're going to subtract our powers and make that into a new x term. So it's going to be 1 minus 1/2, which is just 1/2, so that's quite convenient. So this becomes the integral of 3x to the 1/2 dx. So when you're dividing, remember you subtract your powers, your exponents in that scenario. So this is now in an integratable form. We can go ahead and integrate. So again, increasing the power by 1, so that goes up to a 3/2, dividing by that new power, and then again, just at the end there's almost always an opportunity in integration to tidy up a little. So we're taking the 3/2, turning upside down, flipping it and multiplying by it. So it becomes 3 times 2/3, which is just like this guy actually. So that comes out to be 2x to the 3/2 plus c. So not easy, there's a lot going on in these questions, but the goal is to try and get it always to this integratable form. Let's take a look at this example, the final example on this board. And we can see again there's a couple of issues. The x term is on the denominator and we've got a root going on. So it's a bit like this one, just maybe a little trickier. So we've got the integral here of 7 over x to the 5 to the power of 1/2, because a square root is just a 1/2 power. Remember, we've not integrated at this point, so that's why I'm keeping the integral symbol and the dx. Then we can merge these powers, so that it becomes the integral of 7 over x to the 5/2, and again, we've still not integrated, and in fact it's still not integratable, so we need more steps here, because the x term is still on the denominator, we need to bring it to the top. So this becomes the integral of 7x to the negative 5/2 dx, and now we've finally got it in the ax to the n format, so now we can integrate. So we're going to increase 1 by 1 the power, so the power is currently minus 5/2. We're going to add 1 to that, so again we need to think of that 1 as an equivalent fraction, which will be 2/2. So minus 5 plus 2 is minus 3, so it becomes minus 3/2. So when we add 1 to this power, we get 7x to the minus 3/2, and we're dividing by the new power, so minus 3/2, we've got our plus c on the end. Again, we can tidy this up, so instead of dividing by 3/2, we're going to multiply by 2/3. We can multiply that 2/3 to the 7, so it becomes 14/3, and it would end up being negative 14/3 times x to the minus 3/2 plus c. And again, we could just turn that negative power back into a positive by bringing it back down the bottom of the fraction. So this finally becomes negative 14/3x to the 3/2 plus c. Okay, so let's look at 3 more examples of non-integratable forms. So this guy here, again, non-integratable because there's an x term on the bottom of the fraction. This time we've got a couple of terms on the top, so it's a slightly different scenario, but essentially we're going to use a similar approach to what we saw earlier. There's 2 ways actually you could do this one. You could bring the x to the top and make it an x to the negative 2 and then multiply that to these 2 terms. That's probably not the most efficient way to do it. I would encourage you instead to keep it as keep 2 fractions actually, so splitting this into 2 fractions, so you would get x to the power of 6 over x squared, and then negative 4 over x squared. And again, just be careful not to think that you've performed the integration at that point, or even on the next line, this one's going to need a couple of lines of working to become an integratable form. So this first fraction, we can use the exponent rule for division, which says to subtract your powers. So x to the power of 6 over x squared becomes x to the 6 minus 2, so x to the 4. This one we can just bring the x term to the top, so it becomes 4x to the minus 2, just like we saw earlier. And part of the challenge for students is jumping between these different scenarios and these different exponent rules. It's not easy, it takes a lot of time to get used to these different forms. So these are both now in the correct form. Remember the form that we said earlier we're looking for is ax to the power of n. So ax to the n, every term should be like that to become integratable. So these look good. Remember there's no number a here, but there's basically a 1, like secretly a 1. So these are integratable, so we can use the power rule now. Increasing the power by 1, this becomes x to the power of 5 over 5. Second term becomes negative 4x to the minus 1 because we're adding 1 to the minus 2, divided by minus 1, and then we've got our constant on the end. The first term is pretty much done. There's not really much we can do with that. Some students prefer to write this as 1 over 5, x to the 5, but both of these are fine. This one needs a little manipulation, so a few things going on here. First of all, we've got a negative term, but a negative on the denominator, so they effectively cancel to become a positive. So that's the first thing. And then we've got 4x to the minus 1, but we can write that as 4 over x to the 1, or 4 over x, as it's otherwise known. And then just keep our plus c on the end. So again, good practice to turn these negative final answer powers back positive. And that's mainly because, well, one, your teacher is probably going to tell you to do that. But secondly, because in integration, and differentiation, we're often going to substitute in numbers for the x terms. And if you're substituting a number into a negative power, you could only really do that if it was a calculator question. But sometimes these will be non-calculator, so you need to make it back to a positive power first before you can then integrate. Sub in the value. Okay, so that's the first one. The second one's got a couple of issues. So the product, i.e. the x multiplying to this bracket, that's an issue. That's a non-integratable form. Also the square root, again, like we saw earlier, is non-integratable. So a couple of things to do here to fix this one. Let's just leave the x term in front and we'll change the x to the half power instead of the square root. Like I said earlier, pretty much a no-brainer to do that with any type of root. Not only square roots, any type of root, get rid of those straight away. Now we can multiply out our bracket. So multiplying the x to the half, that's using the multiply exponent rule. Again, remember this x is really an x to the 1. So the multiply exponent rule says add your powers together. So this becomes x to the 1 plus 1/2, which is 1.5, or 3 over 2. And then x times 4, minus 4 is minus 4x. And then we're ready to integrate. So just increasing the power by 1, so this becomes x to the 5 over 2. That's because it's 3 over 2 plus 1, which is 3 over 2 plus 2 over 2, which is 5 over 2. So increasing the power by 1, and then remember to divide by that new power. And the second term becomes 4x. Remember this x is a 1, so it becomes 4x squared over 2. A lot of students think of that as being a 0, and they'll write 4x to the 1 or something like that. Plus c on the end. We can tidy these up. So dividing by 5 over 2 is the same as multiplying by 2 over 5. So this becomes 2 over 5, x to the 5 over 2. 4 divided by 2 is 2, so we get 2x squared plus c. And that's that one done. So these last three examples are all just a little bit longer. They all require 2 or 3 lines of manipulation with the exponent rules before we're ready to integrate. But it's really common for students, if they use 2 or 3 exponent rules, to think by that point that they've integrated, and they actually just forget to integrate. So they might at this stage take off the integral sign thinking that they've integrated already, but all they've done from here to here is turn it into an integratable form and then integrated from here to here. Okay, right, so this guy, again, non-integratable. Let's just deal with the half power square root thing first. So this becomes 1 minus x cubed on the numerator over x to the 1/2 dx. So it's now like the first one. We've gotten rid of that square root and turned it into something like this. So we could again bring the x to the 1/2 to the top, make it an x to the negative 1/2 and multiply that to these two terms. But I think again, I'm going to stick with a fraction method, so splitting this into 2 fractions like this, and then just dealing with the exponent rules from there. This one we can just bring the x up to the top. Again, remember we've not integrated at this point, so this is still going to be an integral of x to the minus 1/2. This one we can use our exponent rules. We're using the divide rule, so we're subtracting the powers. So let's just think about that. So it's going to be 3 take away the power 1/2. So again, making the whole number into an equivalent fraction, so that would be 6 over 2. 3 and 6 over 2 are the same thing, but we need that denominator of 2. 6 over 2 minus 1 over 2, which is otherwise known as 5 over 2. So this becomes x to the 5 over 2 after that manipulation, and that's now in an integratable form. So we can integrate these now term by term. So increasing the power by 1, that goes to x to the positive 1/2 divided by positive 1/2. Second one becomes x to the 5 over 2 plus 1. Think of that 1 again as 2 over 2. 5 plus 2 is 7, so that becomes 7 over 2 divided by 7 over 2 plus c. And then we'll just tidy that up just to finish this question off. Dividing by 1 over 2 is the same as timesing by 2 over 1 or timesing by 2. So that becomes 2x to the 1/2. You could also make that back to a 2 times the square root of x if you wish. So x to the 1/2 or square root of x. This guy again, just flipping that fraction to become 2 over 7 times x to the 7 over 2 plus c. So these questions are not easy. Like I said earlier, a lot of students are okay with the integration part, although integration with fractions is tricky. That brings up a whole other set of problems. But it's more generally the problem is the manipulation of the indices rules and forgetting or not recognizing what is an integratable and a non-integratable form. So really, like a lot of these techniques, practice is the key. So these are some of the common forms, but I would encourage you to practice those just to get really familiar with them.